Okay, so we have discussed a very simple solution to the oscillation problem. But it turns out this is not a very good solution in general. It solves the problem for some cases, but not other cases. So that relates to the non-uniqueness of solutions in some cases. So to give you an example, I'm going to give you a case that is opposite to what I just showed you. Again, it's the Burkas equation. And again, the solution only has 1s and minus 1s. But they are arranged in a different way. So this is minus 1 on the left and 1 on the right, as opposed to 1 on the left and minus 1 on the right. Okay. I'm going to tell you this solution, not as a function of t, is a solution to the Burkas equation. By a solution to the Burkas equation, I mean satisfies the integral form of the Burkas equation. Because whenever there is discontinuity like that, there is no sense talking about the differential forms. Why is this a solution to the integral form of the Burkas equation? F is equal to f of u squared. That's the Burkas equation, right? Why does it satisfy the integral form of the Burkas equation? Huh?
Because where it's continuous, then the u squared is 1, and so the flux are 0, and when it's at the discontinuity, you have the delta f over the u is 0, so it's not, the discontinuity is not moving.
Yes, right, the discontinuity is not moving, that's right. But I mean something, if you go all the way back to the definition of the integral form, you have d dt of any total solution in the control volume is equal to what in this case?
Evaluated.
Yes, in this case, what is it? What is it?
0.
Yeah, 0, right? Because I have f evaluated over L and R, and f is equal to a constant. F is half anywhere in the domain, so this is equal to 0. So I have a stationary solution, right? And what I'm going to tell you is that this is actually not the unique solution starting from this initial condition. I actually have another solution. The other solution is a solution that changes, that doesn't stay as a discontinuity. So let me first describe in a space. So this is an XU plot. Let me describe to you in an XT plot what this solution looks like. Okay, first of all, at this point you have a discontinuity that stays the same, stays here. And on the right hand side, what are the characteristics? What is the slope of the characteristics? It's doing that, right? Everywhere is doing that. On the left hand side, what is the characteristics? It's minus 1. We are going that way, right? So we have characteristics emanating from the shock wave. But I can give you another solution starting from exactly the same initial condition. Okay, so the initial condition tells you that the solution goes this way, right? And there is a discontinuity here. Another solution looks like that. There is this called expansion fan, which means after a while the solution becomes like this. It becomes the steep slope, which is infinite at the t equal to 0, starts to flatten out. and at an even later time the solution will look like that. Which one is a physical solution? Expansion? Why? According to the book,
entropy increases, right?
the entropy would.
Especially the expansion fan versus.
Yeah, the expansion fan actually conserves entropy, and the stationary discontinuity decreases entropy. It's actually negative dissipation. Why is that the case? Because there is information created out of this discontinuity. There is characteristics emanating from this discontinuity. So, a physical equation. Let's think of aerodynamics, for example. The conservation law is an extreme of a dissipative system as the dissipation goes to zero. So a physical shock wave, it actually experiences very small amount of dissipation because the viscosity of air is so small. Compared to the speed and strength of a shock wave, the dissipation is so small that the width of the shock wave is essentially zero. If you have a shock wave in a very dissipative fluid, the width of the shock wave would not be infinitesimal. You would actually have a smooth like discontinuity instead of as a real discontinuity. And imagine if I actually have the grid points to resolve this discontinuity not as a discontinuity but as a very, very steep slope like this. Okay? Then, at a very small region over here, I actually have the characteristic going in all directions, just like that. If I zoom into a region, I am going to be like that, right? Because in between the -1 and 1, I have a very, very tiny region where the characteristics are going in the in-between directions. That is what makes this one as a physical solution, and this as a non-physical solution. A physical solution is the limit of a viscous equation or dissipative equation as the dissipation goes to zero. A non-physical solution is not such a limit. It's a qualitative change from the behavior of any viscous equations. Okay, so that's what dominates which one is a physical solution, which one is a not. And for conservation laws, it's very easy to distinguish. If you have characteristics emanating from the shock wave, from any discontinuity, it is a non-physical solution. If you only have characteristics running into the shock wave, which is like removal of information instead of generation of information, you have a physical solution. Is it clear?
What would it look like going into the shock wave? You're saying that's the right picture if you don't have basically any of these characteristic lines coming into a vertical feature, at least in the time and space plot.
Yeah, in a time and space plot, you cannot have characteristic lines coming from any discontinuity. It's okay to have characteristic going into the discontinuity and disappear. You shouldn't have characteristics appearing out of nowhere from a discontinuity. Okay. Does it make sense? And this is called the entropy condition of a physical solution. The condition is related to entropy in the physical sense, but from a mathematical point of view, it is that characteristics cannot emanate from a discontinuity. And our pure upprinting scheme actually wouldn't really work in that sense. Why? Because if you have the solution like what we drew before, if you have a solution of -1 and 1, and if the discontinuity exactly lies on the interface, okay, no matter which side you upwind, we have a problem. No matter which side you upwind, the f bar is equal to f bar is equal to half over any cells in the domain. And no matter which side you upwind, the interface cell, the interface flux is going to be equal to half, right? So R fi plus half is equal to half for an upwind scheme. So if all the interface flux is equal to the same thing, what happens to the time derivative of the cell averages? It's equal to 0, because according to the integral form of the differential equation, the time derivative of the cell integrals is the difference of the interface flux at adjacent grid points. So I have no time derivative at all. And which solution do I get if I use upwind? The non-physical one, right? Although it is a solution mathematically to the differential equation, but I'm getting a non-physical solution.